So this lesson is on applications of quadratic functions. This is information that you can get from graphs and from tables. So the solutions of a quadratic function are also the blank on the graph. The solutions are the x-intercepts. It's where the graph crosses the x-axis. So if you were to solve a quadratic and get, I don't know, x equals 2 and x equals 5, then you know that that quadratic function crosses the x-axis at 2 and 5. So the solutions are also the x-intercepts. So find the solutions and the x-intercepts of the following functions. So yes, this one is quadratic because he has an x squared. He's not equal to 0 yet, so the first thing I'm going to do is subtract the 28. So x squared minus 3x minus 28. And then I want to try to factor it. And it's a trinomial. So I want the factors of 28 that subtract to give me 3, which are 7 and 4. Signs are different. Bigger number gets the negative. Then I set each one equal to 0 and solve it. So his solutions are 7 and 4, and his x-intercepts are also 7 and 4. Okay, so let's look at B. So B is a quadratic because he has a x squared. He's already equal to 0, so then we're going to try to factor him. And he's a trinomial. I need the factors of 5 that subtract to give me 7. Well, the only factors of 5 are 1 and 5. And in no way, shape, or form are those going to subtract to give me a 7. So this does not factor. Well, because my solutions are also my x-intercepts, what I can do is take my calculator, go to y equals, and graph this guy. So x squared plus 7x minus 5. And then just go graph. And I can see what his x-intercepts are. To find them exactly, I go second calc, and I go to zeros. And first it says get to the left of it. So I'm going to go to this left one over here. There he is. And I'm going to get to the left of him, which would be a little bit above, and hit enter. And then it says to get to the right of him, so that would be a little bit below, and I hit enter. And then it says guess, and I don't want to guess, so I just hit enter again, and it tells me exactly what it is. It is negative 7.65. So then I have to do the same thing. So second calc, down to zeros. I just have to slide over here to the other one. And it wants me to be to the left of it. So to the left of this one is going to be a little bit below it. And then to the right of it's going to be a little bit above it, and I don't want to guess. And that's at 0.65. So those are his x-intercepts, which are also his solutions. Now I got this one from the graph because it does not factor. So I had to graph it. Now, just for kicks, to show you the other one, if I type that into my calculator, x squared minus 3x minus 28, and hit graph, he should cross at -4 and 7, because that's what I found when I solved it. Okay, so let's see what this looks like multiple choice. So if we look at this guy, and it's multiple choice, I'm looking at my answers, and all my answers are ugly. That means I don't even need to try to factor this guy, because if he factors, I'm going to get cute answers like I did in A. If he doesn't factor, I'm going to get ugly answers like I did in B. But I do need to deal with the fact that this is not equal to 0. So I'm going to add 2 and get them equal to 0. And I can tell this is not factor because there are no factors of 2 that add to give me 4, because the only factors of 2 are 1 and 2. And those will add to give me 3, but they won't give me 4. So then I take my calculator and clear him out and go x squared plus 4x plus 2. Go to my graph. There he is. So now I just need to hone in on what those answers are. So I go to 0. I'm going to go to my left point and get to the left of him and hit enter. And I'm going to get to the right of him and hit enter, and I don't want to guess. So negative 3.41. Okay. And I'm going to go second calc to 0. I get to the left of him and get to the right of him, and I don't want to guess. Negative 0.585, so negative 0.59. And let's look. Negative 3.41. There's negative 3.41 and negative 0.59. I like this one. Negative 3.41. No, I don't like that one. And that one doesn't have, so going with this one. So again, to find your solutions and your x-intercepts, you can set it equal to 0 and factor it and get cute answers like that. If he does not factor, you can graph it and find out where his x-intercepts are, because his x-intercepts are also the solutions. Okay. Say is the goalie on the soccer team. A kick he has made is modeled by the graph below, and it shows the height of the ball over a period of 2 seconds. So you can tell when you kick the ball, it goes up, and then it comes back down. 2 seconds, it's hit the ground. The question says, what is the max height? Well, this is my height, so it just wants to know, how high did it go? Well, it went 16 feet. That's it. That's all you have to do for that one. It just wants to know the max height and make sure that you can read a graph. Suppose that that equation represents the value of a car from 1964 to 2002. What year did the car have the least value? Okay, now this is really important too. They're baselining it in 1964. So if x equals 1, we're talking about 1965. X equals 0 is 1964. Now this is a parabola that opens up, so I want to know when it has the least value. So I'm looking for where does it bottom out. I'm going to do this on my calculator. So I'm going to go to y equals 20.8 x squared minus 458.3 x plus 3,500. Ooh, I don't have my plus sign. There we go. Okay, looks good. I could go to my graph, but I don't really want to see the picture. I'm just going to go to my table. Okay, and if we go up here to start at 0, you can see that at 0, we started at 3,500, and you know from before that that is my starting value for parabolas, for quadratic functions. So 3,500, and then what's happening as the years go on? The value of my car is decreasing. Well, I want to know, when does it bottom out? So when does it bottom out and then start to come back up? Because if you keep a car for a really long time, it can increase in value if you take care of it. All right, now look right there, it started to go back up. So it bottomed out at 11 years because it's 975. After that, it starts to go back up. So it takes 11 years. Okay, well, if x equals 0 equals 1964, how do I figure out what year we are? Well, I just have to do 1964 plus 11, and that gives me 1975. Okay, suppose the function represents the total value of an investment after 1985. So X years after 1985. So it looks like we started with $10,000. In what year does the investment have the greatest value? Okay, now if you'll look right here, you'll see that that's negative, and that means that my parabola opens down. So the greatest value is that where it peaks before it starts to go back down, because we want to sell our money when it peaks so we can get the most back on our investment. So I'm going to take my calculator and very carefully type in okay, then I'm going to go to table. And again, if I go back to 0, so I want to know, when does it peak? So I want to know, when does it have the greatest value? I've typed something in wrong. Hold on. Negative 10.4x. Oh, I don't have an x. There it is. There we go. Okay, so now we're typed in. So now let's go to our table. Okay, so at 0, you can see we're starting at $10,000, and here we go. Our money is increasing, increasing. Well, I don't want to sell it yet because it's still increasing in money. So I want to find where it peaks and starts to come back down, because I want to sell this investment when it peaks. Still going up, still going up. That's still higher. Oh, went back down. It went from $443 to $437. So it peaked right there at 18. So 18 years. Well, these are years after 1985. So 1985 plus 18, 2003. So again, I'm just using my table to try to find, on number 3, I tried to find where it bottomed out, where my car had the least value, and the parabola opened up, so that makes sense. And number 4, the parabola opens down. I wanted to find when it had the greatest value. Okay, so now we have this formula. Unfortunately, this is something that you're going to have to memorize, but we're going to use it so much, it's going to be super, super easy. So this is the formula for gravity. And when you are throwing something, and it only works for Earth, V is your initial velocity. And that's the guy that goes with the T. That goes with the T. And this is my starting height. So if you think about it, so I have a 10-year-old daughter. If I throw a softball and she throws a softball, and she's only 10, I should be able to throw it harder than she throws it. So mine would go like that, and hers might go like that. So we have a different parabola shape going on here, and that's because we have a different velocity. So that is the strength, the oomph behind what you're throwing or kicking. And this is your starting height. So I'm taller than she is. So the ball is going to leave my hands up here, and the ball is going to leave her hands down here if you're talking about the ground. So initial means starting, initial velocity. Then this negative 16 t squared, this is just your gravity. Negative because what goes up has to come back down. So a punter punts a football with an initial velocity of 48 feet per second when he's holding it 4 feet above the ground. I just want a formula for this. So f of t equals, now the negative 16t squared stays put because we're on Earth. Plus, now my velocity goes in here, 48t, and then my initial height, 4 feet above the ground. velocity, initial height. And that's it. That's all we're doing right now. A punter can kick a football from the ground with an initial velocity of 48 feet per second. Okay, so on Earth, so negative 16t squared, velocity of 48 feet per second, so 48t, but he's kicking it from the ground. So what is my initial height? 0, because we're 0 feet off the ground. So you can put plus 0, or you can just leave that off because your height is 0. Okay. Number 7. A firework is launched from a cliff overlooking the ocean. The elevation of the fireworks shell in feet above the sea level, t seconds after the launch, is given by that expression. How high is the top of the cliff in feet above the sea level? Well, there's my gravity. I'm on Earth. That's my initial velocity, and that's my initial height. Question says, how high is the top of the cliff? Well, that's where we shot the firework. So it's 63 feet. A baseball is hit off a tee that's 2 feet high. So I know my initial height to be 2 feet. So he's out. He has 2 feet, so does he, and so does he. Upward velocity of 25 feet per second. Bingo. That's it. That's all you got to do. You are throwing a baseball with your younger brother in the backyard. Answer the following questions about the baseball if the ball follows the path modeled by the following quadratic function. Okay, so we know we're on Earth. That's my initial velocity, and that's his initial height. So younger brother releases at 6 feet above the ground. Must be a tall younger brother. How high off the ground is the ball when you release it? Well, that is your initial height, so he's 6 feet. How hard are you throwing the baseball? That's 42 feet per second. That's your velocity. That's that guy right there. How long is the ball in the air before it hits the ground? Okay, so for this, we go to our calculator, and we type this sucker in. And I go to my table, and see, we've already hit the ground by this point. So we'll go, all right, so at 0, you can tell we're at 6, and then 1 second is 32 feet, and 2 seconds is 26 feet, and then at 3 seconds, it's already below ground. So it's happened somewhere in between 2 and 3. So I'm going to go to my table set. I'm going to start it at 2 because I know it happened somewhere in between 2 and 3, and I'm going to go 0.1. And I'm going to go back to my table, and let's see if we can fine tune this and see a little bit more exactly as to when it hits the ground. So we're going to go 2.7 because we're 2 feet above the ground. So we're just going to go 2.7. That's as close as we can. 2.7 seconds. What is the max height? Okay, well, that doesn't have anything to do with time. That has to do with the height. So those are my Y values. So I'm looking for my height to peak. And there it went. Right there. 33.56. So that's my max height. Because that's where it peaks. Other than it's going down. So here, you know, it's still climbing, still climbing. There it peaks, and there it goes back down. So 33.56. And it takes 1.3 seconds for it to peak. What is the height of the ball after it's been in the air for 2 seconds? Okay, 2 seconds. 26 feet. How long has the ball been in the air when it is 20 feet high? Okay, 20 feet high. Okay, about 2.2 seconds. Okay, but let's think about this. 2.2 seconds, that's when it's on its way back down. Doesn't it hit 20 feet on its way up? right there, 0.4. So we actually have two answers because it's going to hit, remember, it peaks at 33.56 feet. So it's going to hit 20 feet on the way up and the way back down. So I want to know how long it takes. So that one's going to be my 0.4 and this is my 2.2. While standing on a cliff 24 feet above the lake, Serena threw a rock with an initial upward velocity of 20 feet per second. That equation gives the height of the rock after t seconds. How many seconds does it take for the rock to hit the water? Okay, so let's say this is the, on Earth, this is the velocity, and this is the starting height. She's on a cliff 24 feet above the lake. And I want to know when it's going to hit the water. So I'm going to go y equals negative 16x squared plus 20x plus 24. Oh, and I'm in decimal mode. So I'm going to go to table set, start at 0, go up by 1. Now let's see. Oh, look, hits the water. Takes it 2 seconds. Splat. And it's hit the water because its height is 0 feet. So it takes exactly 2 seconds for it to hit the water. Didn't have to fine tune that one at all. That function models the approximate height of an object t seconds after its launch. How many seconds does it take for it to hit the ground? Okay, well, let's talk about this one. This one, not on Earth. We are on the moon or we're on Mars, but this has a different gravitational pull. There's my velocity and there's my starting height. And I want it to hit the ground, so I want its height to be 0. So negative 16x squared plus 20x plus 60, except this wasn't a negative 16. It's a negative 5. So negative 5x squared plus 20x plus 60, okay? And I want it to hit the ground, so up, peaks about 80, comes back down, splat hits the ground, takes it 6 seconds. Didn't have to fine tune it at all. Just very nice. Use the following information to answer questions 17 through 19. A company's expenses in millions of dollars can be modeled by the following quadratic equation where t is the time in years the company started. So this is a parabola that opens up. So when they started, looks like they lost a bunch of money and then they bottomed out, but then they started earning money back. And it looks like they started with, now would that be $9? Remember, we're in millions. So they started with $9 million, and then they lost a bunch of money, and then they started to climb back up. So what was the company's minimum expense? Okay, so minimum expense means I'm looking for where does it bottom out. So let's take this, let's type in our equation. Go to my table. So there we start at 9. And I want to know when it bottoms out. Bottoms out right there at 1. Well, 1 for the millions, but it happened 2 years. So 2 years bottomed out at $1 million. And it wants what was the minimum expense. So that would be $1 million. Now this one says, how many years did the company incur its minimum expense? Well, that wants the 2 years. It happened 2 years into this. What was the expense of the company 5 years after it started? $19 million. So really, these are really straightforward. You're going to use your table a lot. Don't forget, I know this part was really easy, but don't forget this part. To solve something like an A, when you can solve it and find its x-intercepts easy by factoring, but in B and C, when it won't factor, you can go to your graph and do the second calc and go to zeros, and you can find where it crosses the x-axis if your answers are decimals.